Hey everyone, tonight we begin with a quiet journey around the moon. Not the loud version of space travel, not the version with flashing graphics, dramatic music, and urgent countdowns. Tonight, we are going to move slowly. We are going to let the story breathe. We are going to follow Artemis II, the mission that carried 4 people away from Earth, around the moon, and safely home again. We will begin on the coast of Florida, with a rocket standing in the evening light. We will rise into orbit, drift outward through deep space, past the far side of the moon, and return through the atmosphere to the ocean below. Before you settle in, like and subscribe only if these quiet journeys help you rest. And if you feel like it, let me know where in the world you are listening from and what time it is for you. There is something comforting about imagining all those different rooms, all those different windows, and the same moon moving above them. Now dim the lights, let the room soften, let your breathing find its own quiet rhythm. Maybe turn on a fan, or let the small sounds around you become part of the background. Because tonight, we are not only talking about a spacecraft, we are talking about distance, patience, engineering, memory, and the strange feeling of seeing Earth from far away. So let the day loosen its grip. The moon is waiting, and our journey begins. The moon is familiar enough to seem ordinary. It appears above streets and fields, above oceans and deserts, above apartment windows and farmhouse roofs. It rises when people are driving home late. It hangs over empty parking lots and quiet gardens. It turns up in songs, calendars, bedtime stories, tide charts, old photographs, and the small drawings children make when they first learn the night sky. Because it is always there, it can feel close. But the moon is not close in any human sense. On average, it is about 238,855 miles from Earth. That number is easy to say and almost impossible to feel. You can fly across an ocean and still be only a tiny fraction of the way there. You can drive for days and days across a continent and barely make a mark on that distance. The moon is close only compared with everything else. It is close compared with Mars, close compared with Jupiter, close compared with the stars. It is our nearest natural companion, but it is still far enough away that Earth itself changes shape behind you when you go there. From the ground, Earth is not an object. Earth is the floor, the air, the weather, the horizon, the gravity in your bones. But from the road to the moon, Earth becomes a sphere, a blue world, a whole world. And that change, more than almost anything else, is why lunar travel still matters. The moon gives us distance from ourselves, and distance sometimes is what makes home visible. For a brief time, human beings went to the moon. The Apollo missions crossed the distance in the late 1960s and early 1970s. Astronauts orbited the moon, walked on its surface, collected rocks, drove across grey plains, and looked back at Earth from a place no living creature had ever stood before. Then the footprints stopped. The last Apollo astronauts left the lunar surface in December 1972. After that, humans remained much closer to home. We built space stations, we launched satellites, we sent robotic spacecraft to every planet in the solar system. We landed machines on Mars, flew past Pluto, sampled asteroids, and sent telescopes into deep space. But no human being traveled around the moon again for more than half a century. That long pause can make the moon feel like a finished chapter, something from old film, something done by a previous generation in grainy footage and white suits. But space exploration is rarely a straight line. It moves forward, pauses, changes direction, learns, waits, and tries again. Technology changes, politics change, budgets change, risks are reconsidered. New generations inherit old dreams and ask whether they are still worth carrying. Artemis II answered that question with motion. It did not land. It did not need to. Its purpose was different. It reopened the crude path beyond low Earth orbit. It tested Orion with people aboard. It took the old road to the moon and proved that, after decades of silence, the route was not gone, only waiting. Artemis is sometimes described as a return to the moon, but that phrase can be a little too simple. The goal is not merely to repeat Apollo. Apollo was brilliant, dangerous, and brief. It proved that human beings could reach the lunar surface and return, but it was not designed to build a lasting rhythm of lunar activity. Artemis is meant to be slower, broader, and more cumulative. It includes the Space Launch System rocket, the Orion spacecraft, ground systems at Kennedy Space Center, new spacesuits, human landing systems, international partnerships, robotic missions, and future plans for surface science. Some parts are already real, some are still being tested, some will change because exploration plans always change when they meet engineering reality. That is important to remember. Space programs are not magic ladders. They are complicated, fragile systems made from hardware, people, funding, politics, physics, and time. Artemis II sat near the center of that system. It was the first crewed Artemis mission. It followed Artemis I, which sent Orion around the moon without people aboard in 2022. Artemis I proved a great deal about the vehicle, but a spacecraft changes in meaning when it carries a crew. With astronauts aboard, the questions become more intimate. Is the cabin livable? Can the systems support human bodies? Can the crew operate the vehicle comfortably enough to do real work? Can the spacecraft bring them home? Artemis II was not simply a trip around the moon. It was a careful test of whether the next era of lunar exploration could begin with people safely inside the machine. Before Artemis II, there was Artemis I. In 2022, Orion flew without a crew on a long test around the moon. It traveled farther into space than any spacecraft built for humans had gone before, entered a distant lunar orbit, and came back to Earth. The mission tested the rocket, spacecraft, heat shield, recovery systems, and many of the procedures needed for future flights. But an uncrewed test, no matter how successful, is only part of the story. A spacecraft can be healthy and still need to be understood as a human place. People bring complexity. They breathe, move, sleep, sweat, eat, ask questions, notice sounds, feel vibration, read displays, make judgment calls, and sometimes experience a machine in ways sensors alone cannot capture. Artemis II added that human layer. It was not the first time Orion flew around the moon, but it was the first time Orion did so with a crew. That meant the life support system was no longer theoretical. The displays were no longer just a design. The seats, suits, procedures, alarms, lighting, volume, stowage, communication loops, and daily routines all became lived experience. This is one of the quiet truths of exploration. A mission can be historic without looking spectacular every minute. Sometimes history is a crew checking a valve. Sometimes it is a flight controller watching a stable number on a screen. Sometimes it is a system doing exactly what it was built to do. Artemis II turned many years of planning into 10 days of reality. And in human spaceflight, reality is the test that matters most. The Artemis II crew was made of 4 people: Reed Wiseman, Victor Glover, Christina Cook, and Jeremy Hansen. Their names belong to the official record, but inside the mission, they were more than names. They were the crew who would turn Orion from a tested spacecraft into a lived-in spacecraft. Each of them brought a different history. Wiseman had already spent time aboard the International Space Station. Glover had flown as part of the commercial crew era and lived in orbit. Cook had completed a long-duration mission and had become known for her scientific work and endurance in space. Hansen, from the Canadian Space Agency, represented the international character of Artemis and became the first Canadian assigned to travel around the moon. But during the flight, all of that background had to become teamwork. A crewed spacecraft is a small society with no room for carelessness. The crew must trust one another's judgment, moods, habits, and discipline. They must know when to speak, when to listen, when to focus, and when to let the spacecraft simply drift through its timeline. They are also test subjects, observers, mechanics, communicators, and witnesses. Their job is to fly the mission. Their other job is to bring back what it felt like. Not just the view, not just the photographs, but the subtle things. How Orion sounded, how the air moved, how the cabin felt after several days, how the human mind responded to seeing Earth become small. Those details would help shape the missions that follow. A commander carries a particular kind of responsibility, not because the commander does everything, but because the commander helps hold the mission together. In a spacecraft, leadership is not loud. It is procedural, steady, and attentive. It lives in the way a checklist is read, the way a crew member is heard, the way a problem is slowed down before it grows. Reed Wiseman served as commander of Artemis II. Before this mission, he had lived and worked aboard the International Space Station. That matters because space is not only a place you visit, it is a place you adapt to. A person who has lived in orbit knows that the extraordinary becomes daily life very quickly. At first, every floating object seems strange. Then it becomes normal. At first, the view of Earth might stop every thought. Then it becomes the window you pass on the way to work. That experience is useful. A lunar mission needs wonder, but it also needs calm. It needs people who can see Earth from space and still finish the next task. It needs people who can respect the beauty without being overwhelmed by it. For Artemis II, the commander's role was not to perform heroism for the camera. It was to help the crew and spacecraft move through the plan. Launch, orbit, checks, burns, coast, flyby, return, re-entry, recovery. Each step had its own rhythm. Each step had its own risks. And leadership in that setting means making the extraordinary feel steady enough to complete. The pilot of a spacecraft does not fly in the way a pilot flies a small aeroplane. There is no air outside most of the journey, no wings biting into the atmosphere, no runway ahead, no simple left or right turn. A spacecraft moves through velocity, orientation, gravity, engine burns, and careful timing. Victor Glover served as pilot of Artemis II. His role was tied to Orion as a vehicle. Its displays, controls, manual flying modes, procedures, and handling all mattered. Even when a spacecraft is highly automated, human understanding remains essential. Automation can follow a plan, but people must understand what the plan means. Manual control tests were part of the mission's purpose. That does not mean the crew was steering casually through space. It means they needed to understand Orion's behavior, how it responded, how it felt, how the controls worked in the real environment beyond Earth, how the displays supported decision-making when the spacecraft was no longer a simulator, no longer a practice run, but a living vehicle with 4 people inside. This is a quiet kind of piloting. It is less like gripping a stick in a storm and more like becoming fluent in the spacecraft's language. The pilot learns its small delays, its responses, its indications, its normal sounds, its expected motions. In a lunar mission, that fluency matters because the crew is far from help. Mission control can advise, teams on Earth can calculate, but inside Orion, the crew is the crew. They are the hands and eyes inside the machine. Christina Cook served as a mission specialist on Artemis II. The phrase mission specialist can sound vague, but in spaceflight, it carries a great deal. It means expertise shaped around the mission's tasks, systems, science, procedures, and crew operations. It means being part of the web of work that turns a spacecraft from a vehicle into a functioning expedition. Cook had already spent a long time in space before Artemis II. Long-duration spaceflight teaches patience. It teaches routine. It teaches the body and mind how to keep working in an environment that never fully becomes natural. It also teaches a person how to notice details over time. That kind of noticing matters on a test flight. A short mission can still be full of observations. How easy is it to move through the cabin? Where do objects tend to drift? Which tasks take longer than expected? Where does the crew need more light, more handholds, more clarity, more comfort? These may sound small, but small things become large during long exploration. A confusing procedure can waste time. A poorly placed object can interfere with work. A subtle discomfort can become fatigue. A noisy system can affect sleep. A crew that sleeps poorly works differently. Artemis II was partly about finding those things early, before lunar landings, before longer missions, before the system became routine. In that sense, the crew were not only flying around the moon, they were helping future astronauts live and work there more safely. Jeremy Hansen flew as a mission specialist from the Canadian Space Agency. His presence aboard Artemis II showed something important about the modern moon program. This was not simply a national replay of Apollo, it was an international step into deep space. Canada has long contributed to human spaceflight, especially through robotics. The Canadarm on the Space Shuttle and Canadarm2 on the International Space Station became symbols of careful, practical partnership in orbit. Those robotic systems helped build, maintain, and operate some of the most complex structures ever assembled in space. Artemis extends that partnership outward. When Hansen traveled around the moon, the achievement belonged not only to one crew or one agency, it belonged to the wider network of people and institutions that make exploration possible. Engineers, trainers, mission planners, medical teams, technicians, recovery crews, contractors, scientists, and international partners all became part of the path. That is how modern spaceflight works. No single person goes to the moon alone. No single spacecraft is built by one pair of hands. Every launch is the visible tip of a very large human structure. For listeners at night, this can be a comforting thought. The mission looks like 4 astronauts in a capsule, but beneath that image are thousands of people cooperating across years. People solving small problems, people checking details, people testing components that may never be famous, but still must work perfectly. The moon was reached by a crew, but the crew was carried by a community. Orion was the crew's home for the journey. Not a large home, not a comfortable room in the way we usually understand comfort. A spacecraft cabin is practical before it is anything else. It must protect, support, organize, and survive. Every object inside Orion had to earn its place. On Earth, we live with extra space without noticing. A drawer can be messy. A table can hold things no one needs. A bedroom can have empty corners. A shelf can collect objects for years. In a spacecraft, every extra gram matters. The cabin must hold equipment, food, water, clothing, emergency gear, tools, cameras, checklists, medical supplies, waste systems, sleeping arrangements, and the crew themselves. It must do this while also giving people room to move, work, and rest in microgravity. that is a design challenge, but it is also a human challenge. A spacecraft is not only a machine, it is an environment. It has sounds, light, textures, routines, and moods. It can feel cramped or efficient, calming or tiring. It can support attention or slowly wear it down. Artemis II helped test Orion as a human place. Can people sleep here? Can they think clearly here? Can they work for days while the Earth shrinks outside? Can the cabin remain a small pocket of order while moving through deep space? Those questions are not dramatic, but they are essential. Exploration depends on small homes that work. Behind the Orion crew module was the European service module. It is easy to focus on the capsule because that is where the astronauts are. But a crew capsule cannot travel alone. It needs power, propulsion, thermal control, and support. It needs a system behind it that quietly keeps the journey possible. The European service module, provided through ESA, gave Orion many of those capabilities. Its solar arrays spread outward like wings, turning sunlight into electrical power. Its systems helped manage temperature, propulsion, and resources. It was not the part of the spacecraft that would return through Earth's atmosphere with the crew. Instead, it served during the mission and then separated before re-entry. There is something almost selfless about a service module. It works for the journey, then lets go. It helps carry the crew through space. Then the crew module continues alone for the dangerous plunge home. This separation of roles is common in spacecraft design. Some parts launch, some push, some protect, some are discarded, some survive. Spaceflight is full of machines that exist for one precise chapter of the mission. That can feel strange from a human point of view. We like objects that last, but rockets and spacecraft often succeed by changing shape. Boosters fall away, stages separate, panels deploy, modules detach. A mission is not one machine doing one thing forever. It is a sequence of machines becoming the next machine. Orion's service module was part of that sequence, a quiet partner on the road to the moon. Before a moon mission becomes motion, it is a tower on the ground. The Space Launch System stood at Launch Complex 39B at Kennedy Space Center, a place already layered with spaceflight history. The pad sits near the Atlantic, where sea-air moves across flat land and water, and where rockets have waited under storms, sunlight, moonlight, and the eyes of people who know how much can depend on a launch day. SLS was built to lift Orion and its crew beyond Earth. A rocket like that is both enormous and delicate. It contains massive tanks, engines, boosters, avionics, plumbing, wiring, valves, sensors, and structural systems. It must tolerate cryogenic propellants, weather, vibration, acoustic energy, and the stress of ascent. From far away, a rocket looks simple: a white column, a pointed top, a machine made for upward motion. Up close, it is almost impossibly complex. And for all that complexity, its most visible work lasts only minutes. Years of design and assembly become a brief climb through the atmosphere. The rocket does not go to the moon itself. It gives Orion the energy it needs to begin. That is the bargain of launch vehicles. They spend themselves so something else can continue. On the pad before liftoff, all of that energy is still potential. The vehicle is quiet, held by structures, watched by teams, surrounded by procedures. The moon is far away. The rocket is still on Earth. And between them is the moment everyone is waiting for. A countdown is not just a clock. It is a way of organizing attention. In the final hours before launch, thousands of details converge. Weather must be acceptable. The rocket must be fueled. Ground systems must be ready. Communications must be clear. The spacecraft must report that it is healthy. The crew must be strapped in, suited, connected, and prepared for a moment they have rehearsed many times but experienced only once. For listeners on the ground, a countdown can feel dramatic. For the people working it, the drama is held inside procedure. Call-outs happen, teams answer, systems are polled, holds may occur, data is reviewed. A launch is not allowed to happen simply because everyone wants it to happen. It happens because the vehicle, the weather, the range, the crew, and the teams all agree through data and procedure that it can. Inside Orion, the crew waits. This waiting is a special kind of patience. There is no casual walking around, no stepping outside for air, no changing your mind about small discomforts. The body is held in the seat. The suit is on. The spacecraft is alive around you. And below, the rocket is slowly becoming ready to stop being a rocket on Earth and become a vehicle in flight. Launch day contains many emotions, but the spacecraft does not care about emotion. It cares about conditions, pressure, temperature, timing, guidance, fuel, power. When those conditions align, the countdown becomes motion, and motion becomes ascent. On April 1st, 2026, Artemis II lifted off. The engines and boosters turned stored chemical energy into light, heat, pressure, and sound. The rocket rose from Kennedy Space Center with the Orion spacecraft at its top, carrying 4 people into the sky. Launch is the loudest part of a quiet journey. The ground shakes, the exhaust blooms. The vehicle climbs slowly at first, almost impossibly slowly for something so powerful. Then it gathers speed. The tower falls away. The coast falls away. The Atlantic curves beneath it. The rocket begins to leave behind the thick, lower atmosphere where weather lives. Inside the spacecraft, launch is not a view from a distance. It is force. The crew feels acceleration through the body. Vibration travels through structure. Voices come through headsets. Displays change. The mission timeline moves quickly. Training takes over. A rocket does not simply go up. It arcs. It turns. It builds horizontal velocity. To reach orbit, a spacecraft must move sideways so fast that as it falls toward Earth, the planet curves away beneath it. That is orbit. A continuous fall around the world. Minutes after liftoff, parts of the launch vehicle had already done their work. Boosters separated, stages completed their roles. The mission became smaller in shape and larger in meaning. The enormous Tower of Fire had one purpose: to place Orion and its crew on the path where the moon could become reachable. And then, above the atmosphere, the first great noise of the journey gave way to the quieter work of spaceflight. After launch, Earth changes quickly. The familiar world becomes curved. Clouds stop being weather overhead and become patterns below. The blue of the ocean becomes brighter against the blackness above. The atmosphere, so enormous from the ground, begins to look like a thin, glowing line. For the Artemis II crew, the first hours in space were not only about wonder, they were about checking Orion. A crewed test flight must confirm that the spacecraft is ready before it commits to deeper space. Earth orbit gives the mission a place to listen carefully to the vehicle. Systems are checked. Navigation is confirmed. Communications are tested. The crew begins adapting to weightlessness. Mission control watches data stream back from the spacecraft. This is the practical beauty of an early orbit phase. Home is still near, but space has begun. The crew can see the planet, but they are no longer part of its ordinary surface life. They are inside a sealed cabin, moving through vacuum, dependent on systems that must work continuously. That dependence can sound unsettling, but in a good spacecraft, it becomes rhythm. Fans move air, Electronics hum softly, displays glow, objects float if they are not secured. The crew learns again, as every space crew does, that up and down are habits, not laws. The first view of Earth is famous because it is beautiful, but it is also instructive. It shows the crew what they have left, and it shows them what they must return to. Earth orbit can feel like a waiting room between worlds. You are no longer on Earth, but you have not yet gone far. The planet still dominates every view. The spacecraft circles above oceans, deserts, storms, mountains, and cities. Sunrise and sunset can arrive quickly, one after another, as the vehicle moves around the globe. For Artemis II, this time near Earth mattered. A mission around the moon cannot be treated like a simple departure. Before leaving, the spacecraft and crew must be ready. Teams must be confident in the life support system, the communications links, the guidance, the power, and the crew's ability to operate the spacecraft. In a sleep story, this is a quiet section. No dramatic event is needed. The spacecraft is awake. The crew is adjusting. Earth turns below. Imagine the night side passing underneath. City lights trace coastlines and rivers. Lightning flashes inside clouds. The thin atmosphere catches sunlight at the edge of the world. Somewhere below, people are eating dinner, turning off lamps, walking dogs, driving home, checking messages, and looking up without knowing exactly when Orion passes overhead. From orbit, ordinary life becomes part of the view. That is one of the strange gifts of spaceflight. It turns daily life into something planetary. The crew is not yet far enough for Earth to look small, but they are far enough to see that all of our ordinary nights are happening on one turning sphere. Soon, that sphere will begin to shrink. But for a while, Orion remains near home, making sure it is ready to leave. Every spacecraft has to be learned. Even after years of simulation, the real cabin is its own place. The way light falls across a panel, the way a sound travels, the way a strap behaves in weightlessness, the way the body turns when a hand touches a wall, the way sleep feels when there is no bed in the ordinary sense. The Artemis II crew had trained for Orion, but training and flight are not identical. In flight, the spacecraft has personality. It is not alive, of course, but people naturally learn machines through sensation. A healthy hum becomes familiar. A normal vibration becomes background. A particular motion after a thruster firing becomes expected. The crew builds a working relationship with the vehicle. This relationship matters because lunar missions are too complex to be experienced only as passengers. The astronauts must know how to work inside Orion when everything is normal, and how to respond if something is not. They must know where objects are, how to move, how to communicate, how to rest, how to preserve attention, and how to keep the cabin organized. Organization is not a small thing in space. A loose item can become a problem. A misplaced tool wastes time. A cluttered cabin can make simple tasks harder. In a small spacecraft, good habits are part of safety. So the crew learns the cabin, and the cabin, in a sense, teaches them. It teaches economy of motion. It teaches patience. It teaches that in deep space, comfort is not luxury. Comfort is one of the ways people stay capable. A spacecraft must make a tiny version of Earth, not a full Earth, not weather, oceans, soil, trees, and open sky, but enough of Earth to keep human bodies alive. It must hold pressure. It must provide oxygen. It must remove carbon dioxide. It must control temperature. It must manage humidity. It must keep the air moving. It must provide water, handle waste, and protect the crew from the vacuum outside. On Earth, these things are so constant that we almost never think about them. The air is just there. Pressure is just there. Warmth is usually a matter of clothing, walls, sunlight, or a thermostat. In Orion, None of that is automatic. Every breath depends on engineering. That makes life support one of the most intimate technologies in the mission. It is not distant from the crew. It is inside every inhale, every exhale, every moment of rest. The system has to work when the crew is awake and when they are sleeping. It has to work while the spacecraft is near Earth and while it is moving through deep space. Artemis II tested these systems with people aboard. That is a profound step. A reading on the ground can say a system is performing well, but a crew can say how the air feels, whether the cabin is comfortable, whether humidity builds, whether sleep is affected, whether the vehicle supports the body as well as the numbers suggest. In human spaceflight, data and experience belong together. Both came home from Artemis II. There are no roads to the moon. There are only paths made from motion. To travel from Earth to the moon, Orion had to follow a carefully planned trajectory. The spacecraft was not aimed at the moon as if the moon was standing still. The moon is always moving. Earth is moving too. The spacecraft leaves a rotating planet to meet an orbiting world, while gravity reshapes the path the entire time. This is why lunar travel is more like choreography than driving. The timing matters. The direction matters. The speed matters. The burns matter. A small change early can become a large difference later. Navigation is the art of knowing where you are going, and how gravity will bend the space between. Artemis II used a path that carried Orion around the moon and back toward Earth. This kind of journey depends on physics doing part of the work. The moon's gravity helps shape the return. There is elegance in that. A spacecraft does not need to fight the universe at every moment. It can use the universe. It can borrow the curves that gravity naturally provides. For the crew, the path is invisible. They do not see a glowing line ahead of them. They see Earth, moon, sun, stars, displays, and numbers. The path exists in mathematics, in guidance systems, in mission control calculations, and in the actual motion of the spacecraft. A road made of numbers, a road through darkness. At some point, a lunar mission must stop circling Earth and begin leaving it. This is one of the great emotional thresholds of the journey. The engine burn is technical. It has a planned duration, direction, and purpose. It changes the spacecraft's energy, raising its path from Earth orbit into the long arc toward the moon. But beneath the engineering is a simple human feeling. After the burn, home begins to fall behind. Not suddenly, not like a door closing. The change is gradual. Earth is still visible. Communications still connect the crew to mission control. The spacecraft is still part of a carefully monitored system, but the geometry has changed. The crew is no longer simply orbiting Earth. They are outbound. The moon is no longer only the object in the night sky. It is the destination built into the spacecraft's path. Each hour adds distance. Each hour makes Earth appear more complete and less like the world of ground-level experience. This is where the journey begins to feel lunar. For listeners settling into sleep, imagine it quietly. No need for drama, just a small spacecraft turning in sunlight, an engine firing for a measured time, a planet behind it, and the moon somewhere ahead. The burn ends. The spacecraft coasts, and now speed becomes patience. A lunar journey is not all fire. Most of it is falling gracefully along a path that was chosen before launch. The engine gives the push, gravity writes the curve, and Orion follows. As Orion moved outward, Earth began to shrink. This is one of the simplest sentences in spaceflight and one of the hardest to absorb. Earth is the largest thing in human life. It is so large that we usually do not see it at all. We see pieces, a street, a room, a field, a cloud, a shoreline, a city at night. We do not normally see the whole planet because we are inside the experience of it. Deep space changes that. At first, Earth fills the view, then it becomes a sphere, then a smaller sphere. The continents soften, weather systems dominate. The atmosphere becomes a faint blue rim, almost impossibly thin. The night side holds clusters of city light. The day side reflects sunlight from oceans and clouds. From far away, Earth looks calm. This calm is partly an illusion. Down there, storms are moving. People are arguing, laughing, working, grieving, cooking, sleeping, being born, and saying goodbye. The whole intensity of human life is still happening, but from deep space, it becomes quiet. This quiet is not emptiness, it is perspective. The farther Orion traveled, the more Earth could be seen as one place, not as maps and borders, not as separate weather reports or separate histories, one luminous world carrying everyone. Many astronauts have described how powerful this view can be. Artemis II brought that experience back into the present for a new crew, for a new century, for all of us watching from home. Deep space can look empty, but it is not nothing. There is sunlight, even far from Earth. There is radiation from the sun and from beyond the solar system. There are tiny particles, magnetic fields, temperature extremes, and the constant presence of gravity. There is darkness, but not absence. For a spacecraft, this environment matters. Low Earth orbit sits within some protection from Earth's magnetic field. A mission around the Moon moves beyond much of that familiar shield. Radiation becomes a more important concern. Solar activity must be watched. Space weather is not weather in the ordinary sense, but it can affect spacecraft and crews. Artemis II helped gather experience in this environment. How do the spacecraft systems perform beyond Earth? How does the radiation environment compare with expectations? How do operations change when the crew is farther away? These questions matter because later missions will ask astronauts to do more. Rendezvous, docking, lunar landing operations, surface work, and longer stays. Before those missions, it helps to understand the simpler act of traveling out and back with a crew aboard. Deep space also changes communication. The farther the spacecraft moves, the longer signals take to travel. The delay is still small on a lunar mission compared with Mars, but it is real. Voices and data cross a distance that human bodies cannot cross quickly. The crew remains connected to Earth, but not in the ordinary way. Connection becomes radio, antennas, tracking stations, protocols, and patience. In deep space, even conversation becomes engineering. Most of a space mission is not made of famous moments. It is made of routine. The crew eats, the crew sleeps, the crew checks systems, the crew talks with mission control. They adjust equipment, they document observations. They manage small tasks that would seem ordinary if they were not happening between Earth and the Moon. This routine is not filler, it is the mission. Human beings need rhythm to function. Even in deep space, perhaps especially in deep space, the day must be organized. Work periods, rest periods, meals, communications, exercise if possible, medical checks, housekeeping, and personal time all help the crew remain steady. A spacecraft cabin can become cluttered quickly if routine slips. Sleep can become uneven if the schedule drifts. Attention can fray if too many small discomforts accumulate. So the mission builds structure. There is something restful about that idea. Even on a journey around the Moon, people still need ordinary things: food, water, sleep, conversation, a place to put equipment, a way to clean up, a way to mark the passing of time. The extraordinary does not replace the ordinary. It rests on top of it. Inside Orion, the crew lived within that balance. Outside the window was the impossible, Earth shrinking, moon approaching, stars steady in blackness. Inside the cabin was the practical, straps, packets, checklists, screens, voices, schedules. Exploration is not only the view, it is also the discipline that lets people keep looking. Sleep in space is a science of its own. On Earth, sleep is helped by gravity. Your body rests on a surface. The bed holds you. A pillow supports your head. Blankets stay where they are placed. The room has an up, a down, and a familiar stillness. In microgravity, the body does not settle in the same way. A sleeping astronaut may be gently secured so they do not drift. Arms do not naturally fall downward. The head does not press into a pillow. The sense of position can change. The spacecraft continues to hum around the sleeper. Light and darkness may not follow an ordinary day. On a lunar mission, the psychology is different too. Imagine trying to sleep while knowing that Earth is no longer beneath you in the normal way. It is behind you, outside the spacecraft, visible through a window as a world in the distance. The moon is ahead. The cabin is safe because systems are working. The crew can rest because other people are awake, watching data, listening, ready. Sleep becomes an act of trust. Trust in the spacecraft, trust in the crew, trust in mission control, trust in the mathematics of the path. For a sleep documentary, this is a gentle place to pause. 4 people inside a small cabin, the lights dim, the spacecraft drifting through a darkness so wide that speed looks like stillness. The moon growing larger, whether anyone is awake to see it or not, and Earth quiet and blue, keeping its own slow turn behind them. At first, the moon is a bright disk, then it becomes a world. As Orion approached, the lunar surface would have grown more detailed. Dark plains and pale highlands sharpened. Crater rims became visible. Shadows revealed depth. The smooth face seen from Earth began to show its roughness. The moon is not smooth, not soft, not gentle in its geology. It is a record of impacts. For billions of years, objects struck its surface. Dust, stones, boulders, asteroids, pieces left over from the early solar system. Without thick air to burn them up, without rain to wash the scars away, without active plate tectonics to recycle the surface as Earth does, the moon kept many of those marks. This makes it scientifically precious. Earth is active. Earth heals and destroys evidence. Its crust moves. Its oceans reshape coastlines. Its atmosphere changes rock. Life itself alters chemistry. The moon preserves, not perfectly. Nothing in the solar system is perfectly preserved. But compared with Earth, the moon is an ancient archive lying in plain sight. Artemis II did not land to read that archive with boots and tools, but it carried humans close enough to see the landscape as landscape again. That matters. Because the moon is not only a symbol in the sky, it is a place with a surface, a history, a shape, and a silence older than life on Earth. As Orion approached, that place filled the windows. The moon always shows Earth nearly the same face. This is not because the moon does not rotate. It does rotate. It turns once in about the same time it takes to orbit Earth. This relationship is called tidal locking. Because of it, the near side remains familiar to us. The far side, for most of human history, was hidden. Tidal locking is a result of gravity acting over time. Earth's pull raised tides in the moon long ago. Not oceans of water, but distortions in the moon's body. Those interactions gradually slowed the moon's rotation until one side stayed oriented toward Earth. The result is a kind of celestial partnership. The Moon orbits Earth while keeping one hemisphere turned our way. We see its phases because sunlight strikes it from different angles as it moves around us. A new moon is near the direction of the sun. A full moon is opposite the sun in our sky. The surface is the same world, but the light changes. This is why the far side has such a strong hold on imagination. It is not permanently dark. It is not cursed or mysterious in the way old phrases sometimes imply. It is simply turned away. Spacecraft revealed it. Photographs mapped it. Robotic missions studied it. But for a crew passing behind the moon, the far side is still a powerful experience. Because when the moon blocks Earth, it also blocks direct radio contact. The geometry of an orbit becomes silence, and the hidden face of the moon becomes the wall between a crew and home. The far side of the moon is rougher in many places than the face we know. Its surface is heavily cratered, marked by old impacts and highlands. It lacks the same broad pattern of dark volcanic plains that make the near side so recognizable from Earth. To pass over it is to see a world no human eye saw directly until the space age. During Artemis II, Orion's path carried the crew around the far side. For a time, the moon itself came between the spacecraft and Earth. The crew continued the mission, but direct communication with home was interrupted by the most ancient kind of barrier: rock and distance. There is no need to make that moment frightening. It is beautiful enough as it is. Imagine the spacecraft moving behind the moon, the grey surface below, the black sky above, no blue planet in sight, no direct voice from Earth. Only the crew, Orion, the mission timeline, and the moon's far side passing beneath them. This silence is not symbolic to the radio system. It is just physics. Radio waves travel in straight lines. The moon blocks the line. The signal cannot pass through. But for human beings, physics becomes feeling. A few minutes without direct connection can carry the weight of distance. It reminds us that even the nearest world is truly separate from Earth. Then Orion continues along its path. The moon's curve shifts, the line of sight returns, and eventually Earth comes back into view. NASA reported that Artemis II passed about 4,067 miles above the lunar surface at closest approach. That is still a vast height by earthly standards. It is farther than many long airplane routes. It is far above the moon's mountains and crater rims, but compared with the distance from Earth, it is intimate. The moon stops being only a destination and becomes terrain. At that distance, the eye can begin to sense the shape of the surface. Craters overlap. Some rims are sharp, others are softened by time and later impacts. Shadows gather in low places. Sunlit slopes reveal relief that is hidden when the moon is only a pale disk in the night sky. The crew did not descend. They did not land. They swept around the moon on a flyby path designed to bring them home. But a flyby can still be profound. It is a meeting without stopping. A close pass between a human spacecraft and an ancient world. The spacecraft arrives, listens to gravity, follows the planned curve, and begins returning to Earth. In those moments near the moon, the mission condensed many years into a view. The design of Orion, the power of SLS, the training of the crew, the calculations of the trajectory, the work of mission control, the legacy of Apollo, the future of Artemis, all of it passed above the lunar surface in one small spacecraft. And below, the moon remained what it has always been: silent, cratered, patient, and waiting. During the mission, NASA reported that the Artemis II crew traveled about 252,756 miles from Earth at their farthest point. That distance made the mission record-setting for human travel from our planet. Records can sound like sports statistics, but this one carries a different feeling. It is not only about going farther, it is about what farther means. At that distance, Earth is no longer the world beneath your feet. It is a bright planet in black space. Radio signals take longer to cross the gap. The moon is not a decoration in the sky, it is a nearby world. The crew is inside a spacecraft that must remain healthy because there is no quick rescue, no nearby runway, no simple return to ordinary conditions. The record belongs to the crew, but also to the vehicle and the teams behind it. To travel that far and return safely is a systems achievement. It means launch worked, trajectory worked, life support worked, communications worked, navigation worked, reentry worked, recovery worked. Every part of that chain matters because the chain is only as strong as its weakest link. From the outside, a record distance is a number. From the inside, it is a place where Earth looks small. Perhaps that is the more important record. Not simply how far humans went, but how clearly they could see home from there. A blue world, a crew inside Orion, the moon nearby, and the rest of space stretching outward without end. During the lunar flyby, Orion captured striking views of the moon backlit by the sun. From the spacecraft's vantage point, the geometry of sun, moon, and observer created a rare and beautiful alignment. The moon, so often seen from Earth as a glowing object, became a dark shape edged by light. This is one of the quiet pleasures of spaceflight. It changes familiar things by changing where you stand. From Earth, the moon reflects sunlight toward us. It brightens the night. It shows phases as it moves through its orbit. From Orion, near the moon, the same object can become a silhouette, a world blocking the sun, a black circle with sunlight around its edge, a reminder that brightness and darkness are often only matters of position. No new moon was created in that moment. No new physics appeared. The beauty came from perspective. That is true of much of lunar flight. The moon is the same moon that rises over a quiet street. Earth is the same Earth that holds your bed, your room, your city, and your morning. But from deep space, familiar bodies arrange themselves in unfamiliar ways. The eye sees the mechanics of the solar system not as a diagram, but as a lived geometry. Sun, moon, spacecraft, Earth somewhere beyond. For a few moments, the sky becomes a lesson in alignment, and the lesson is silent. When Earth appears beyond the moon, it changes the meaning of both worlds. The lunar surface is grey, dry, and ancient. It has no blue weather, no moving oceans, no forests, no clouds throwing shadows over continents. Its silence is almost complete. Then Earth enters the view. Blue, white, bright, alive. The contrast is overwhelming, even when described gently. Earth looks delicate because it is surrounded by darkness. It looks small because the moon gives it scale. It looks unified because no borders are visible from that distance. This view has shaped human thought before. Apollo 8's Earthrise photograph became one of the defining images of the 20th century. It helped many people feel in one glance that Earth is not an endless stage for human events. It is a planet. Artemis II brought human beings back to that kind of perspective. The crew did not need to land to experience the power of the view. Sometimes orbiting the moon is enough. Sometimes seeing Earth above a lifeless horizon is enough. The sight tells a quiet truth. The moon is a place we can visit. Earth is the place that made us. The moon can teach us about history, geology, exploration, and the future. Earth teaches us value. From lunar distance, Our planet is not guaranteed, not ordinary, not replaceable. It is luminous and rare, and everyone you have ever known lives on it. A space mission is also a conversation. The crew sees something, the spacecraft records something, instruments measure something, cameras capture light, antennas send data, ground stations listen, mission control receives, processes, and shares what comes back. During Artemis II, images from the moon and deep space traveled home as signals. That idea is worth resting with. A photograph is not carried back like a postcard in a pocket. It becomes data, encoded and transmitted across the distance between worlds. Radio waves leave the spacecraft, cross space at the speed of light, and arrive at Earth, where machines and people turn them back into images. The result may appear on a screen almost casually: a moon photo, a view of Earth, a spacecraft image. But behind that casual appearance is a chain of astonishing reliability. The camera must work. The storage must work. The spacecraft's communication system must work. The antenna geometry must work. The receiving station on Earth must be ready. The data must be handled correctly. Only then can people at home see what the crew saw. This is how exploration becomes shared. 4 people can go around the moon, but millions can receive the view. And for a sleep listener, there is something calming about imagining those signals crossing the dark. No hurry, no sound, just information moving through space. Light turned into data, distance turned into connection. After the lunar flyby, the emotional direction of the mission changed. The spacecraft was still following its planned path, but the feeling became return. The moon began to recede, Earth began to grow. There is a special quiet in that turn. The outward journey carries anticipation. The flyby carries awe. The return carries concentration. Because coming home from the moon is not passive. The spacecraft must remain healthy. Its trajectory must stay correct. Communications must continue. The crew must prepare for re-entry. Mission control must watch the numbers and the weather and the recovery plans. The systems that have worked for days must keep working. The path home is shaped by gravity, but it still belongs to the mission. Every hour brings Earth closer. At first, Earth is a blue disk in the distance. Then it grows. Details return. The planet becomes less like an object and more like a destination. For the crew, this must be a strange reversal. The world they left becomes the world they are approaching. The planet that became small becomes large again. The atmosphere that looked thin from far away becomes the shield they must enter. In lunar flight, Earth changes roles several times. It is home, then a planet, then a target, then home again. The turn back is where those meanings begin to overlap, and Orion, small against the dark, carries them all. Before re-entry, the cabin becomes focused. Loose items must be secured. The crew must be suited and strapped in. Procedures must be followed carefully. The spacecraft must be oriented correctly. The mission shifts from days of travel to minutes of intense physics. Re-entry is one of the reasons the moon is difficult. Leaving Earth takes enormous energy, but returning from deep space means arriving with enormous energy too. A spacecraft coming back from the moon is moving much faster than a spacecraft returning from low Earth orbit. That speed must be managed. The atmosphere will do much of the work, but it will do it violently. Air molecules will slam into the spacecraft. Heat will build. Plasma will form. The heat shield will protect the crew by absorbing and carrying away energy. Inside, the crew cannot see all of this as an outside observer might. They experience acceleration, sound, vibration, communication call-outs, and the discipline of remaining ready. The spacecraft that was a small home now becomes a returning capsule. This is another transformation in the mission. Orion launched as the top of a rocket. It became a spacecraft in orbit. It became a deep space vessel on the way to the moon. It became a lunar flyby craft. Now it becomes a re-entry vehicle. One mission, many identities. Each identity depends on the one before it. And as Earth fills more of the view, the crew prepares to trust the final design. The heat shield below them, the parachutes packed and waiting, the ocean far beneath. A heat shield is a very patient object. For most of the mission, it waits. It does not guide the spacecraft to the moon. It does not provide air. It does not make the cabin comfortable. It does not take photographs or speak with Earth. It simply remains attached to the bottom of the crew module, silent and ready for the few minutes when its work becomes essential. During re-entry, speed becomes heat. The spacecraft meets the upper atmosphere at tremendous velocity. Air compresses and heats around it. A glowing plasma sheath forms. Temperatures rise far beyond what the crew cabin could survive without protection. The heat shield's job is not to remain unchanged. It is designed to lose material in a controlled way. This process, called ablation, carries heat away from the spacecraft. The shield sacrifices part of itself so the crew module can remain safe. There is something elegant about that design. Protection through controlled loss. The heat shield is one of the great quiet heroes of a lunar mission. It does not make the journey look beautiful, it makes the return possible. For Artemis II, this mattered deeply. Artemis I had tested Orion's heat shield without a crew. Artemis II brought the human stakes into the same physics. The shield had to protect not only an empty cabin, but 4 people coming home from the moon. The spacecraft entered, the heat built. The shield did its work, and Earth, which had been a blue sphere in the distance, became atmosphere, gravity, and return. After the heat of re-entry comes the slow opening of parachutes. This part of the mission looks gentle from a distance, but it is a carefully staged sequence. Parachutes do not simply appear all at once. They deploy in phases, each one reducing speed, stabilizing the capsule, and preparing for the next step. The spacecraft has already survived launch, deep space, the lunar flyby, the return coast, and re-entry heating. But the mission is not over. A safe landing still depends on fabric, lines, pyrotechnics, timing, sensors, air, and design. Parachutes are soft objects doing hard work. There is something almost old-fashioned about them. After all, the engines, computers, antennas, heat shielding, and orbital mechanics, the final descent depends on canopies filling with air. Spaceflight often combines the futuristic and the ancient in this way. A spacecraft travels around the moon, then comes home by using the atmosphere and falling toward the sea under cloth. The crew, strapped inside, waits through the sequence. Main parachutes open. The descent slows. The ocean grows closer. From the outside, cameras show a capsule hanging beneath bright shapes in the sky. From the inside, the crew feels the final motions before water contact. The parachutes are not the end of danger, but they are a sign that the most fiery part is over. They are the mission exhaling. After days between worlds, Orion is no longer moving like a deep space vehicle. It is descending toward Earth as something almost familiar. A capsule under a sky, a crew coming home. On April 10, 2026, Orion splashed down in the Pacific Ocean off the coast of California. After the flame of launch, the quiet of deep space, the grey moon, the black sky, and the heat of re-entry, the mission ended in water. There was something deeply human about that image. A spacecraft built with modern materials, guided by computers, launched by one of the most powerful rockets ever flown, returns at last to the sea. The oldest surface on Earth waits for one of our newest machines. Splashdown is not a casual moment. The capsule meets the water. The spacecraft must remain stable. Recovery teams move in. Procedures continue. The crew waits for the next steps. The The ocean is beautiful, but it is also an environment that must be handled with care. Still, compared with re-entry, splashdown feels like relief. The spacecraft is no longer glowing with heat. It is no longer crossing the atmosphere at enormous speed. It is floating. The sky is above it. The waves move around it. Help is nearby. For the crew, Earth is no longer a distant sphere. It is water against the capsule. It is gravity in the body. It is voices outside. It is the knowledge that the journey around the moon has become a completed mission. For everyone watching, splashdown closes the loop. The path that began on a launch pad returns to the planet, not to land, but to ocean. Not with a thunderous ending, but with a floating capsule and the first quiet minutes of being home. Recovery is part of the mission too. It can look like an aftermath, but it is planned with the same seriousness as launch. The capsule must be secured. The crew must be helped out safely. Medical checks must begin. Hardware must be protected. The spacecraft must be brought aboard and returned for inspection. A mission does not end when the parachutes open. It ends when the crew is safe and the data is in hand. Recovery teams train for this moment long before splashdown. They practice approaching the capsule, stabilizing it, communicating with the crew, and handling the spacecraft in the ocean environment. The sea is never just scenery. It moves, it changes, it must be respected. For Artemis II, recovery also had symbolic weight. 4 people had traveled around the moon and returned. Their spacecraft carried the marks of that journey. The heat shield had done its work. The parachutes had done their work. The cabin held the lived experience of the crew. Now, all of that returned to human hands. Engineers would inspect. Doctors would evaluate. Mission teams would analyze. The crew would tell the story from inside the spacecraft. This is another kind of exploration. The careful work after the dramatic part is over. What did the vehicle experience? What did the crew notice? What can be improved before the next mission? The ocean recovery is therefore not merely a rescue scene. It is the beginning of learning. The journey comes home. Then the mission begins to teach. After a mission like Artemis II, the spacecraft becomes evidence. Every sensor record matters. Temperatures, pressures, vibrations, communication performance, life support data, navigation performance, propulsion behavior, cabin conditions, heat shield response, parachute sequence, and recovery details all become part of the story. The public remembers launch and splashdown. Engineers remember traces, a mark on a surface, a reading slightly higher than expected, a component that performed beautifully, a procedure that took longer than planned, a crew comment about lighting, sound, layout, or timing. This is how exploration becomes safer. Not by assuming success means perfection, but by studying success carefully. Artemis II's job was to provide confidence for what comes next. Confidence does not mean pretending nothing could go wrong. It means understanding what happened well enough to make the next risk more manageable. In that sense, the mission continued after the crew came home. Teams began reviewing data from Orion, SLS, ground systems, and recovery operations. They compared predictions with reality. They looked for lessons. They turned a 10-day flight into months and years of improvement. This is the quieter side of space history. No single image captures it. It happens in meetings, labs, reports, inspections, simulations, and updated procedures. But without it, exploration would become memory instead of progress. The dream needs the data. The moon view needs the spreadsheet. The story needs the review. And the next crew needs everything this crew learned. Artemis II proved a chain. That is the simplest way to say it. Launch had to work. Earth orbit operations had to work. Orion had to support the crew. The path to the moon had to work. The lunar flyby had to work. Communications had to work. Navigation had to work. The return path had to work. Re-entry had to work. Parachutes had to work. Splashdown and recovery had to work. A crewed lunar mission is not one success. It is many successes connected in the correct order. If any major link fails, the mission changes. That is why test flights matter. They let a program learn whether the links hold together, not just in design, but in reality. Artemis II did not prove everything about returning to the lunar surface. It did not test a lunar lander with crew. It did not test walking on the moon in new spacesuits. It did not build a surface base or operate at the South Pole. But it proved something necessary before those things. It proved that the crewed transportation system could take people around the moon and bring them home. That is not a small statement. It reopens capability. It gives engineers data. It gives future crews experience to learn from. It gives the public a new memory of humans near the moon, not as history, but as present tense. The mission's power is not only that it went far, it is that it came back with knowledge. Some missions are destinations, others are bridges. Artemis II was a bridge mission. It connected the uncrewed Artemis I test to future crewed operations. It connected the Apollo past to the Artemis future. It connected low Earth orbit experience to deep space travel. It connected old lunar memory to new lunar plans. Bridge missions can be misunderstood because they are not always the most dramatic on the surface. They prepare, they verify, they reduce uncertainty, they make the next step less reckless. In exploration, that is a noble role. A bridge does not exist for itself alone. It exists so that crossing becomes possible. Artemis II crossed a gap in experience that had been open since the Apollo era. Human beings had not traveled around the moon for decades. The hardware was new, the teams were new, the world was new, the moon was the same. That contrast is part of the beauty. The ancient moon waiting while human systems changed around it. Artemis II did not need to be the final form of lunar exploration. It needed to carry people safely across the first crewed deep space step of the program, and it did. For a sleep listener, this is a reassuring shape. Not every journey has to finish the whole dream. Some journeys simply make the next journey possible. Sometimes that is enough. Sometimes that is everything. After Artemis II, NASA's updated plan did not jump straight to a crewed lunar landing. In 2026, NASA described a more cautious sequence. Under that plan, Artemis III would serve as a test mission in Earth orbit for the Human Landing System and spacesuit operations. The idea is similar in spirit to an Apollo-era lesson. Test complex pieces together before asking them to work at the moon. That may sound less glamorous than landing immediately, but it is the kind of adjustment that makes exploration more realistic. A lunar landing is not only Orion. It requires a lander, spacesuits, docking or transfer operations, surface procedures, communications, power, life support, ascent, rendezvous, and return. Each of those pieces must work alone, and then they must work together. Testing integrated operations closer to Earth can reduce risk before committing crews to the lunar surface. This is not a retreat from the moon. It is a way of approaching it with more discipline. Artemis IV, under the updated plan, became the targeted mission for returning astronauts to the lunar surface in 2028. Plans can still change. Space programs always live with uncertainty, but the larger direction remains clear. Artemis II was not the end of the story. It was part of a sequence meant to make lunar exploration repeatable, safer, and more sustainable. The moon does not reward impatience. It rewards preparation. and Artemis II gave that preparation a human beginning. Future Artemis surface missions are especially interested in the lunar South Pole. This region is different from the broad equatorial areas visited by Apollo. Near the poles, the sun stays low along the horizon. Shadows stretch long across the surface. Some crater interiors may remain in permanent shadow, cold enough to preserve water ice and other volatile materials over immense spans of time. Water ice matters for science. It may help tell the story of comets, asteroids, solar wind, and the movement of volatile materials through the inner solar system. It may preserve clues about how the Moon has interacted with space for billions of years. Water also matters for exploration. If it can be accessed and used, it may support future crews with drinking water, oxygen, and possibly propellant ingredients. That does not mean lunar ice is simple to mine or guaranteed to solve every problem. The Moon is harsh. The cold traps are dark and extremely cold. The terrain can be difficult. Dust can damage equipment. Power and communications require careful planning. But the possibility changes the Moon from a place to visit into a place where longer activity might be supported. Artemis II did not go to the South Pole. It did not land anywhere. But by proving the crude flyby system, it helped prepare the chain of missions that may eventually work there. In that sense, a journey around the Moon is connected to footprints not yet made. A quiet orbit is connected to future surface lights in long polar shadows. The Moon's surface is covered in dust, not soft dust like household dust, and not sand shaped by water and wind. Lunar dust is made from rock, broken down by impacts and space weathering. Its grains can be sharp, clingy, and difficult. Apollo astronauts learned this directly. Dust stuck to suits. It came into the lunar module. It smelled strange when brought inside, likely because fresh reactive surfaces met cabin air. It scratched, coated, and interfered. For future lunar missions, dust remains one of the practical challenges of working on the Moon. This is a good reminder that exploration is often less romantic up close. From Earth, the Moon is silver and serene. On the surface, it is abrasive, airless, and extreme. Temperatures swing. Shadows are black. Sunlight is harsh. There is no atmosphere to soften the day or carry sound. A footprint can remain for an extraordinary length of time because there is no rain to wash it away. Artemis II did not touch the dust, but its story leads toward missions that will. Those future missions must deal not only with grand questions, but with small grains. How does dust affect seals? How does it affect joints? How does it affect lungs if brought into a habitat? How do astronauts keep equipment clean enough to work? The Moon is majestic from far away. It is practical and difficult up close. Both truths matter, and both make it worth understanding slowly. The Moon matters even when no one is traveling to it. Its gravity helps raise tides in Earth's oceans. The tides are shaped by many factors, including coastlines, ocean basins, the sun, and Earth's rotation. But the Moon is the central partner in that daily movement of water. Over deep time, the Moon has also influenced Earth's rotation and axial stability. Its presence has helped shape the environment in which life evolved. It is not merely an ornament in the sky, it is part of the Earth system. This connection is easy to forget because moonlight feels gentle. But the Moon is not just light, it is gravity. It is timekeeping, it is geology, it is history. It is a witness to early solar system events that Earth has mostly erased. When Artemis II traveled around the Moon, it was not visiting an unrelated object. It was visiting Earth's companion, a world tied to our planet by origin, orbit, gravity, and memory. The Moon may have formed after a giant impact early in Earth's history, when debris from that collision gathered into the body we see today. Scientists continue to refine the details, but the broad idea connects the Moon's existence to Earth's own violent beginning. So, a journey around the Moon is also a journey into Earth's past. The grey world in the sky is part of our story. It helped shape our nights. It helped shape our oceans. It may help us understand how our planet became itself. That is why the Moon still pulls at science as well as imagination. The greatest view from a Moon mission may not be the Moon. It may be Earth. That is not because the Moon is unimportant. The Moon is extraordinary, ancient, silent, scientifically rich, and close enough to teach us how to explore beyond our own world. But Earth, from lunar distance, carries a different kind of knowledge. It shows everything alive that we know of in one small sphere. Every forest, every reef, every desert, every city, every sleeping child, every memory, every language, every song, everything human and everything more than human, held in one blue and white world. From the surface, Earth can feel too large to care for. Its problems can feel scattered, divided, and overwhelming. From the Moon, Earth is one place. Fragile not because it is weak, but because it is finite. Artemis II gave 4 people that view directly, and gave the rest of us a chance to imagine it again. This is one reason crewed spaceflight still matters, even in an age of powerful robotic explorers. Robots can go farther, they can endure more, they can do science in places humans cannot yet survive. But humans carry meaning back in a particular way. They tell us what it felt like. They remind us that exploration is not only about reaching outward, it is also about returning with a clearer view of home. One of the quietest parts of a Moon mission is also one of the most important: listening. On Earth, enormous antennas wait for the spacecraft's signal. They stand in wide open places, far from city noise, turning slowly beneath the sky. Their work is patient. They do not look dramatic in the way a launch looks dramatic. They do not roar. They do not throw flame across the ground. They simply point. They listen for a human-made whisper crossing hundreds of thousands of miles. For Artemis II, communication was more than conversation. It was navigation, health monitoring, data, voice, engineering, and reassurance. Every signal carried information: cabin status, system performance, crew reports, tracking data, images. The small details that tell a flight control team how a spacecraft is doing while it moves through a place where no repair truck can arrive. The farther Orion traveled, the more delicate that connection felt. Radio waves move at the speed of light, which is astonishingly fast. But space is large enough to make even light seem thoughtful. Near the Moon, a signal takes a little over a second to cross the gap between spacecraft and Earth. That delay is small, but it is real. A question leaves Earth. The answer comes back just after the moment has already changed. It is a gentle reminder of distance. Inside Orion, the crew could speak to Earth, but they were also beyond Earth in a way that no phone call can quite erase. And on the ground, every voice from the spacecraft was proof of connection. The Moon journey was not only 4 people flying outward, it was an entire planet listening. Space travel changes the ordinary rhythm of a day. On Earth, morning and night arrive without being asked. The sun rises, the air warms, streets fill, shadows move. The body receives thousands of small instructions from light, temperature, meals, sounds, and habit. In a spacecraft, those instructions become artificial. There is still time, of course. There are clocks, schedules, checklists, mission events and carefully planned work periods, but the natural day becomes complicated. In low Earth orbit, astronauts can see many sunrises and sunsets in a single day. On the way to the Moon, the rhythm changes again. Earth grows smaller. The Sun is constant unless blocked by the spacecraft, the Moon, or Earth itself. Night becomes not a place, but a direction. So crews rely on routine. They eat at planned times. They sleep when the mission plan says to sleep. They dim lights, secure equipment, and let the cabin become as restful as a test spacecraft can be. This sounds simple until you imagine the mind inside it. You are in a small vehicle. You know where you are going. You know millions of people may be watching parts of the mission from home. You know the machine around you is still being proven, and outside the window, Earth is becoming a small blue world in black space. Sleep under those conditions is an achievement of trust. Trust in training, trust in the vehicle, trust in the people awake on the ground, trust in the quiet mathematics that says the spacecraft is where it should be. For Artemis II, rest was not separate from the mission, it was part of the mission. Human beings do not become machines in space. They still need darkness. They still need calm. They still need the courage to close their eyes. A spacecraft window is a small thing with an enormous job. It is not just glass. It is structure, pressure boundary, thermal protection, optical surface, inspection point, camera frame, and emotional anchor. Through it, astronauts can see what instruments describe in numbers. A window turns data into presence. For much of a mission, flight controllers know exactly where the spacecraft is through tracking and navigation. They know speed, position, attitude, trajectory, fuel, pressure, temperature, and electrical status. They can see the mission through streams of information moving across screens, but the crew can look out and say, there it is. There is Earth. There is the Moon. There is the blackness between them. That human sentence matters. It matters because exploration is not only the collection of measurements, it is also the act of witnessing. Cameras can capture images, and they do so beautifully. But when a person frames a view from inside a spacecraft, the image carries another layer. Someone was there. Someone turned toward the window. Someone held still for a moment and let the sight arrive. During Artemis II, images and video from the mission became part of the public experience. People on Earth could see pieces of the journey almost as if looking over the crew's shoulder. Not everything needs to be explained at once. Sometimes a view is enough. Earth hanging in space, the curve of the Moon, sunlight striking metal, a cabin reflection on a window. Small details like these can do what numbers cannot. They can make distance emotional. They can make engineering feel intimate. And for a sleep documentary, they offer something especially gentle. A window in the dark, a quiet view, a world slowly moving past. It is natural to ask why Artemis II did not land. After all, the Moon is the place in the story that draws the eye. It is the bright destination, the old dream, the grey world waiting beyond the window. A flyby can sound, at first, like stopping at the doorway and turning around. But spaceflight is built in steps for a reason. Landing on the Moon is not one challenge. It is many challenges stacked together. You need the rocket to leave Earth. You need the spacecraft to support the crew. You need navigation across deep space. You need communication. You need life support. You need thermal control. You need propulsion. You need reentry protection. You need recovery. And then, for a landing, you need an entirely additional chain of machines and operations. A lander, spacesuits, surface power, surface communications, dust protection, ascent from the Moon, rendezvous, docking, emergency planning. Every added step multiplies complexity. Artemis II had a narrower purpose, and that purpose was valuable. It asked whether the crude Orion system could take people beyond low Earth orbit, carry them around the moon, and bring them safely home. That is not a small question. It is the question that must be answered before bolder questions can be asked responsibly. Sometimes exploration looks like restraint. Sometimes the brave thing is not to do everything at once. Sometimes the mission that does not land is the mission that makes later landings possible. Artemis II was that kind of journey, not a final act, a careful crossing, a bridge of fire, metal, water, data, and patience. Beyond Artemis II, the lunar story becomes more crowded. Not crowded in a loud way, but crowded with systems. A future crewed landing is not simply Orion plus courage. It requires a whole set of new machines working together with unusual precision. The spacecraft that carries astronauts around the moon is one part. The system that takes them down to the surface is another. The suits that keep them alive outside are another. The communications that connect surface, orbit, and Earth are another. The tools, rovers, experiments, cameras, batteries, procedures, and emergency plans are all part of the same web. This is why Artemis II mattered even without a landing. It tested a core piece of that web while leaving other pieces to be tested in their own time. Future lunar landing systems must do something extremely difficult. They must leave lunar orbit, descend toward a surface with no atmosphere, manage engine plume interactions with dust and rock, touch down safely, become a home for astronauts during surface operations, and then launch again from the moon to reconnect with the ride home. Every one of those verbs is a world of engineering. Descend, touch down, support, launch, rendezvous, return. And the spacesuits are spacecraft too, in miniature. They must hold pressure, remove carbon dioxide, regulate temperature, allow movement, protect against dust, and let a human being work in a place where the environment offers no forgiveness at all. From a distance, a future moon landing may look like a single graceful event, but underneath, it will be thousands of quiet decisions. Artemis II helped clear the path for those decisions by proving what it could prove first. The rest would come step by step. The Artemis story is not only American, it is international, and that matters. The Orion spacecraft uses a service module provided by the European Space Agency. That module supplies critical support, including propulsion, power, thermal control, and resources needed by the crew module. It is easy, from the outside, to think of a spacecraft as one national object, one clean machine with one origin. But real spacecraft are collaborations. They carry the work of many places: factories, laboratories, test stands, clean rooms, transport teams, software teams, engineers, technicians, safety reviewers, and mission planners all leave fingerprints on the final vehicle. Artemis II also carried a Canadian astronaut around the moon, making the journey part of a wider human story. Canada has long contributed robotics and expertise to spaceflight, from space station systems to lunar partnership planning. In Artemis II, that partnership became personal and visible. One of the gentle truths of space exploration is that no country owns the night sky. The moon rises over everyone. It does not check borders before reflecting sunlight. It hangs above languages, governments, coastlines, and histories. And when a crew travels around it, the meaning is larger than any single patch of ground below. International cooperation in space is never simple. It involves agreements, budgets, priorities, delays, and compromises. But when it works, it does something rare. It turns exploration into a shared project rather than a solitary boast. That shared quality fits the moon. A common object, a common light, a common silence. Artemis II moved through that silence, carrying more than 4 people. It carried partnerships. And behind those partnerships, the quiet hope that reaching outward can teach us to work together here. Human journeys to the moon do not replace robotic exploration. They depend on it. Long before a crew reaches a place, machines can map, measure, photograph, sample, orbit, and survive. Robotic spacecraft can stay where humans cannot yet stay. They can watch the moon through long cycles of sunlight and darkness. They can examine radiation, temperature, terrain, gravity, and resources with patience. The moon we understand today is partly a world built from robotic eyes. Orbiters have mapped its surface in extraordinary detail. They have studied mineral patterns, topography, temperatures, and permanently shadowed regions. Landers and impact missions have searched for clues about water and volatile materials. Future robotic deliveries are expected to keep adding to that knowledge, especially in places where human missions may one day work. This partnership between robots and people is not a competition. It is a rhythm. Robots scout, humans interpret, adapt, repair, improvise, and carry meaning. Robots can do the long waiting. Humans can do the strange noticing. A person on the moon can turn toward an unexpected rock, change a plan, describe a texture, react to a color, and make decisions with the full weight of experience. A robot can help make that moment safer and more informed. Artemis II was a human mission, but it stood on a foundation of robotic exploration. Every map mattered. Every measurement mattered. Every prior orbit made the road a little less unknown. And still, even with all that knowledge, the moon remains mysterious enough to invite return. That is one of the beautiful things about science. Understanding does not always end wonder. Often, it deepens it. Near the moon's poles, there are places where sunlight may not reach for extremely long periods. These are permanently shadowed regions, often inside deep craters where the sun stays low along the horizon. The rims may glow in harsh light, while the interiors remain black and bitterly cold. They are sometimes called cold traps. The name is simple and almost poetic. Molecules that wander into these frozen places can become stuck there. Over long spans of time, water ice and other volatile materials may collect in shadows that act like natural vaults. For lunar science, these regions are valuable because they may preserve a record of impacts, cometary material, solar wind interactions, and the moon's long exposure to space. For future exploration, water ice could become important as drinking water, oxygen, or possibly rocket propellant after processing. But the cold traps are not easy treasure chests. They are dark. They are extremely cold. They may be difficult to reach. Power is harder where sunlight is absent. Communication can be complicated by crater walls and terrain. Machines become brittle. Instruments must survive conditions that challenge even carefully designed systems. This is where the moon becomes less like a symbol and more like a real place. A place with shadows that matter. A place where a ridge can be useful because it receives light. A place where a crater floor can hold secrets because it has been protected from the sun. Artemis II did not enter those shadows. It remained a journey around the moon, not onto it. But its success supported the larger effort to understand how experts might one day work near them, not quickly, not casually, carefully, with machines, maps, practice, and respect for the cold. The moon is not Mars. It is much closer, much smaller, and very different in history, gravity, atmosphere, temperature, and surface conditions. But the Moon may still become a practice ground for deeper space. Not because it is easy, because it is difficult in useful ways. On the Moon, astronauts must deal with vacuum, radiation, dust, delayed communication, limited supplies, harsh lighting, and the constant need to make machines work far from ordinary help. Those challenges echo some of the problems future crews would face on longer journeys, including missions toward Mars. But the Moon has one major advantage. It is close enough for learning to be faster. A radio signal takes only a little over a second each way. A mission can return in days rather than months. If plans fail, engineers can study them, change them, and try again within a human timescale. Mars is far less forgiving. Depending on orbital positions, communication delays can stretch from several minutes to more than 20 minutes one way. A crew there would be much more independent. Supplies would be harder to send. Rescue would not be simple. So the Moon offers a place to practice living beyond Earth without pretending that all deep space is the same. It is a school, but a severe one. A testing ground made of dust, silence, and sunlight. Artemis II was one of the early lessons in that school. How does the crewed spacecraft behave? How do people feel inside it? How does the ground team support them? How does the whole system respond when the journey is no longer close to Earth? Before Mars can be more than a dream, questions like these have to be answered slowly, one mission at a time. Going to the Moon is dramatic. Coming home is precise. A spacecraft returning from lunar distance does not simply fall back to Earth in a casual way. It must arrive at the right angle, the right speed, and the right corridor in the atmosphere. Too steep, and heating and deceleration become dangerous. Too shallow, and the spacecraft can skip away from the atmosphere or fail to slow as planned. The return is a kind of needle threaded through air. From far away, Earth looks generous. It is huge and bright, surrounded by atmosphere, covered in ocean. But for a returning spacecraft, the safe path is narrow. Mission planners spend years understanding that path before the crew ever launches. The Moon's gravity shapes the journey. Earth's gravity pulls. The spacecraft's propulsion adjusts. Tracking data refines the plan. Small burns can make large differences later. A correction made quietly in deep space can determine where the capsule meets the atmosphere days afterward. This is one reason spaceflight can feel almost musical. Events are separated by silence, but connected by timing. A burn, a coast, a measurement, a correction, another coast. Then the sudden violence of reentry. Artemis II's return depended on all of this. The peaceful image of a capsule under parachutes is the final visible answer to a long chain of invisible mathematics. Before the parachutes, there is the trajectory. Before the splashdown, there is the corridor. Before the ocean, there is the angle. And before the angle, there are people on Earth and in space making sure the numbers remain kind. It is a quiet form of care. Care written in velocity, gravity, heat, and time. After all the fire and distance, the journey ends in water. This is one of the oldest and strangest contrasts in human spaceflight. A rocket leaves Earth on a pillar of flame, crosses the border into space, travels around another world, returns through a heated shield of plasma, and then becomes a small floating object in the ocean. The Pacific waits, broad, dark, and moving. Recovery teams wait too, arranged with care long before the capsule arrives. Ships, aircraft, divers, medical teams, engineers, and support crews all have their roles. They train for the moment when a spacecraft is no longer a point on a screen, but a real object rocking on waves. Splashdown looks simple from far away. A capsule descends under parachutes. It touches the water. The mission is home. But the work continues. The vehicle must be secured. The crew must be checked. The hatch must be handled safely. The spacecraft may be hot, wet, unstable, or surrounded by hardware that needs careful attention. Even after landing, spaceflight asks for discipline. The ocean ending also carries a certain softness. After days beyond Earth, the first world the crew physically touches is not land, but water. The same water shaped by tides. The same water moved, in part, by the moon they have just circled. That connection is quiet and beautiful. The moon lifts the ocean. The ocean receives the moon travelers. And somewhere above, the moon continues its orbit, indifferent and luminous, while people in boats move toward the capsule with practiced hands. Exploration often ends this way, not with a final heroic pose, but with careful recovery. A hatch, a hand, a breath of Earth air, and the long journey becoming memory. There is a temptation with space exploration to rush the story, to ask only when the next landing will happen, when the next launch will happen, when the next milestone will happen. But the moon does not move at the speed of impatience. Neither does engineering. Every space program exists inside delay, revision, testing, retesting, investigation, redesign, and the stubborn refusal of physics to care about schedules. This can be frustrating from the outside. It can feel slow. It can feel as if the future is always moving a little farther away. But slowness can be protective. It gives engineers time to find flaws while flaws are still on the ground. It gives teams time to practice emergencies before they become real. It gives hardware time to reveal weaknesses. It gives crews time to prepare their bodies and minds for events that cannot be improvised casually. Artemis II was part of this slow courage. It did not need to be the loudest mission imaginable. It needed to be careful. It needed to learn. It needed to bring its crew home and leave behind knowledge useful for everything that follows. There is humility in that. The moon has waited billions of years. It can wait for good engineering. And perhaps there is something restful in that thought. The future does not have to arrive all at once. It can arrive by checks, by launches, by coast phases, by quiet corrections, by safe returns, step by step, orbit by orbit, mission by mission, not a sprint into the dark, a patient road through it. So tonight, as you settle deeper into the quiet, imagine the journey one more time. A rocket standing on the Florida coast, 4 people inside a small spacecraft, the engines lighting, the tower falling away, Earth orbit blue and bright, the careful checks before departure, the burn that sends Orion outward, Earth shrinking behind the windows, the moon growing ahead, the far side passing below in radio silence, the close flyby over grey terrain, Earth returning above the lunar horizon, the long coast home, the heat shield meeting the atmosphere, the parachutes opening, the Pacific Ocean waiting below, and then the simple fact of return. Artemis II was a mission of engineering, but it was also a mission of perspective. It reminded us that the moon is not only an old story from history books, it is still there, still moving around Earth, still lifting tides, still reflecting sunlight into quiet rooms, still waiting above the night. And Earth is still here too, blue, bright, alive, and easy to take for granted until you see it from far away. That may be the gentlest gift of a journey around the moon. Not the record, not the distance, not even the spacecraft, but the view back home. So rest now, if you can. Let the moon continue its slow orbit. Let Earth turn beneath the night. Let the the stars remain steady and far away, and let this quiet journey fade softly into sleep.